Have you ever looked at a system of equations like this and felt completely overwhelmed? Two equations, two unknowns, and no idea where to start? Well, I have great news for you. By the end of this video series, you'll be able to solve systems like this with confidence using a powerful technique called the substitution method. Welcome to this comprehensive tutorial on solving systems of equations using the substitution method. I'm here to guide you through every step of this fundamental algebraic technique. First, what exactly is a system of equations? Simply put, it's a collection of two or more equations that share the same variables. Our goal is to find the values of these variables that satisfy all equations simultaneously. The substitution method is one of the most reliable techniques for solving these systems. The basic idea is beautifully simple. We solve one equation for one variable, then substitute that expression into the other equation. This transforms our system of two equations with two unknowns into a single equation with just one unknown, which is much easier to solve. Once we find that variable, we can work backwards to find the other one. Throughout this video series, we'll break down the substitution method into 5 clear, manageable steps. Each step builds on the previous one, making the entire process systematic and reliable. Each step serves a specific purpose and follows logically from the previous one. By mastering these 5 steps, you'll have a powerful tool for solving any system of linear equations, no matter how complex it might initially appear. In the following sections, we'll dive deep into each of these steps, work through detailed examples, and by the end, you'll be solving systems of equations with confidence and precision. Are you ready to master the substitution method? Before we dive into the substitution method, we need to understand exactly what a system of equations is and why we need special methods to solve them. A system of equations is a set of two or more equations that contain the same variables. Think of it as multiple mathematical statements that must all be true at the same time. Here's a simple example of a system. We have two equations, 2x plus y equals 7 and x minus y equals 2. Notice that both equations contain the same variables, x and y. The key feature of a system is that the same variables appear in multiple equations. Here, both x and y appear in both equations. This is what makes them a connected system rather than separate, unrelated equations. Our goal when solving a system is to find values for x and y that satisfy both equations simultaneously. This means we need to find numbers that, when substituted for x and y, make both equations true at the same time. For this system, the solution is x equals 3 and y equals 1. But how do we know this is correct? We need to verify that these values satisfy both equations. To verify, we substitute x equals 3 and y equals 1 into the first equation. 2 times 3 plus 1 equals 6 plus 1, which equals 7. This matches our equation, so the first equation is satisfied. Now for the second equation, 3 minus 1 equals 2. This also matches our equation perfectly. Since both equations are satisfied by the same values, we have found the correct solution to our system. This verification process shows us exactly what it means for values to satisfy a system simultaneously. Both equations must be true when we use the same x and y values. You might wonder why we need special methods like substitution to solve systems. Why can't we just guess and check until we find the right answer? First, guessing and checking is inefficient and unreliable, especially for more complex systems. Second, we need systematic approaches that always work, regardless of the numbers involved. Finally, mathematical methods give us exact answers rather than approximations. The substitution method provides a reliable, step-by-step process to solve any system of equations. In the following sections, we'll learn exactly how this method works and practice applying it to various types of problems. The first and most crucial step in the substitution method is to isolate one variable in one of your equations. This means we want to get one variable by itself on one side of the equation. When we isolate a variable, we perform algebraic operations to get that variable alone on one side of the equation. For example, if we have x plus y equals 5, we can isolate x by subtracting y from both sides. Starting with x plus y equals 5, we subtract y from both sides. This gives us x plus y minus y equals 5 minus y. Simplifying the left side, we get x equals 5 minus y. Now x is isolated. Here's a key strategy. Always look for a variable that has a coefficient of 1. This means the number in front of the variable is 1, or there's no number written at all. This makes the isolation process much simpler. In this system, x plus 2y equals 7 and 3x minus y equals 1. We can see that x in the first equation has coefficient 1, and y in the second equation also has coefficient 1. Either variable would be easy to isolate. We'll choose to isolate y from the second equation since it already has coefficient 1, starting with 3x minus y equals 1. Starting with 3x minus y equals 1, we subtract 3x from both sides to get negative y equals 1 minus 3x. Finally, we multiply both sides by negative 1 to get y equals 3x minus 1. Now y is isolated. Sometimes no variable has coefficient 1. In this system, 2x plus 3y equals 8 and 4x minus 2y equals 6. All coefficients are greater than 1. We should choose the variable that requires the simplest operation to isolate. The negative 2y term is easiest because we only need to divide by negative 2. Starting with 4x minus 2y equals 6, we first subtract 4x from both sides, then divide by negative 2. Here are the most common mistakes students make when isolating variables. First, forgetting to apply operations to both sides of the equation. Second, making sign errors when moving terms from one side to the other. Third, not simplifying fractions completely. Remember, whatever you do to one side of the equation, you must do to the other side. To summarize step 1 of the substitution method. First, choose a variable with coefficient 1 if possible. If none exist, pick the variable that's easiest to isolate. Use inverse operations to get the variable by itself, and always remember to apply the same operations to both sides of the equation. Mastering this first step sets you up for success in the remaining steps of substitution. Now that we've isolated a variable in step 1, we move to step 2, substitution. This is where we take the expression we found and substitute it into the other equation. The key word here is other equation. We substitute our isolated expression into the equation we did not use for isolation. From our previous step, we isolated y and found that y equals 5 minus 2x. Now we need to use this expression. Here's our other equation, 3x minus y equals 0. This is where we will substitute our expression for y. Now watch carefully as we substitute. We replace every y in the second equation with our expression 5 minus 2x. We replace y with the entire expression 5 minus 2x. Notice that we put parentheses around the expression to keep it together. Parentheses are crucial when substituting. Without them, we might incorrectly distribute the negative sign, leading to the wrong equation. Notice what happened. We started with an equation containing both x and y. After substitution, we now have an equation with only x. This is exactly what we wanted to achieve. Remember these key points for step 2. Substitute into the other equation. Always use parentheses around your expression, and the result should be an equation with only one variable. This sets us up perfectly for step 3, where we'll solve for that single variable. Now we reach step 3 of the substitution method. At this point, we have successfully created a single equation with just one variable. Our task now is to solve this equation using standard algebraic techniques. Solving means using standard algebraic techniques to isolate the variable. This includes combining like terms, distributing, and performing inverse operations. The key is to work systematically and not skip steps. Here's our first example. After substitution, we have the equation 5x equals 10. This is a simple linear equation that we can solve in one step. To isolate x, we divide both sides by 5. This is the inverse operation of multiplication. Simplifying, we get x equals 2. We have successfully found the value of our first variable. Here's a more complex example. After substitution, we have 3x minus the quantity 2x plus 4 equals 6. This requires multiple steps to solve. Step 1, we distribute the negative sign. Negative times 2x gives us negative 2x, and negative times 4 gives us negative 4. Step 2, we combine like terms. 3x minus 2x equals x, so we have x minus 4 equals 6. Step 3, we add 4 to both sides to isolate x. This gives us x equals 10. Another variable successfully solved. Here's our most complex example. We have 2 times the quantity x plus 3 minus 5x equals negative 9. This requires multiple algebraic steps. First, we distribute the 2. 2 times x is 2x, and 2 times 3 is 6. So we have 2x plus 6 minus 5x equals negative 9. Next, we combine like terms. 2x minus 5x equals negative 3x. So we have negative 3x plus 6 equals negative 9. We subtract 6 from both sides to get negative 3x equals negative 15. Then we divide both sides by negative 3 to get x equals 5. Perfect. Remember these key points when solving in step 3. Use standard algebra techniques, work step by step without skipping, distribute first, then combine like terms, use inverse operations, and always check your arithmetic. Once you solve for one variable, you're halfway to completing the entire system. Now we reach step 4, back substitute. This is where we take the value we just found and use it to determine our second variable. Remember, in step 3, we solve for one variable. For example, we might have found that x equals 3. Now we need to find the other variable. We have two options. We can use the isolated expression we created in step 1, or we can substitute into either of the original equations. Here's a concrete example. We started with this system of equations. In step 1, we isolated y to get y equals 11 minus 2x. Then in step 3, we found that x equals 4. Now we need to substitute x equals 4 back to find y. Notice how we highlight the value we're about to use. We substitute x equals 4 into our isolated expression. Y equals 11 minus 2 times 4. Now we perform the arithmetic. 2 times 4 equals 8, so we have y equals 11 minus 8. Finally, 11 minus 8 equals 3, so y equals 3. Now we have our complete solution. X equals 4 and y equals 3, giving us the ordered pair 4, 3. Alternatively, we could substitute x equals 4 directly into either of our original equations. Both will give us the same answer. The second equation looks simpler, so we'll choose that one. We substitute x equals 4 to get 4 minus y equals 1. Subtracting 4 from both sides gives us negative y equals negative 3. Multiplying both sides by negative 1 gives us y equals 3. Same answer. Here are the key points to remember about back substitution. Always use the value you found in step 3. Choose the equation that looks easiest to work with. This is often the isolated expression from step 1. Remember that both original equations will give you the same result, so pick whichever looks simpler. And always perform your arithmetic carefully to avoid errors. Back substitution is the crucial step that gives us our complete solution. Once we have both variable values, we're ready to check our answer in step 5. Step 5 is crucial but often overlooked by students. Checking your solution. This verification step ensures your answer is correct and builds confidence in your mathematical reasoning. Checking your solution serves multiple important purposes. It catches any arithmetic errors you might have made, confirms that your solution actually satisfies both original equations, builds your confidence in mathematical problem solving, and represents complete, thorough mathematical work. Here's our checking process. We have our original system of equations, and we found that x equals 1 and y equals 3. Now we must substitute these values back into both original equations to verify they work. First, we check equation 1, 2x plus y equals 5. We substitute x equals 1 and y equals 3. This gives us 2 times 1 plus 3 equals 5. Simplifying, 2 plus 3 equals 5, which gives us 5 equals 5. This is true, so our solution satisfies the first equation. Now we check equation 2, 3x minus y equals 0. Substituting our values, 3 times 1 minus 3 equals 0. This simplifies to 3 minus 3 equals 0, which gives us 0 equals 0. This is also true, confirming our solution is correct. Since both equations are satisfied, we express our final solution as an ordered pair. The solution is 1, 3, where 1 is the x-coordinate and 3 is the y-coordinate. This ordered pair represents the point where both equations intersect on a coordinate plane. Be aware of these common mistakes when checking solutions. Never check only one equation, you must verify both. Work carefully to avoid arithmetic errors during substitution. Always use the original equations, not any simplified versions. And remember to express your final answer as an ordered pair. To summarize, step 5, Substitute both x and y values into both original equations, verify that both equations produce true statements, and express your verified solution as an ordered pair. This checking step is essential for mathematical accuracy and completeness. Now that we've learned all the steps of the substitution method, it's time to put everything together with a complete example problem. We'll work through this step by step, just like you would on a test or homework assignment. Here's our system of equations. We have 2x plus y equals 5 and 3x minus y equals 0. Our goal is to find the values of x and y that satisfy both equations simultaneously. Step 1. We need to isolate a variable. Looking at our equations, I notice that y has a coefficient of 1 in the first equation, making it the easiest to isolate. Let's solve the first equation for y. Starting with 2x plus y equals 5, I'll subtract 2x from both sides to isolate y. This gives us y equals 5 minus 2x. Perfect. Now we have y expressed in terms of x. Step 2. Now we substitute our expression for y into the second equation. We have 3x minus y equals 0, and we know that y equals 5 minus 2x. Substituting y equals 5 minus 2x into the second equation, we get 3x minus, and here I'll substitute the entire expression, 5 minus 2x equals 0. Notice the parentheses around 5 minus 2x. This is crucial for maintaining the correct signs. Step 3. Now we solve for x, starting with 3x minus the quantity 5 minus 2x equals 0. First, I'll distribute the negative sign. The minus sign in front of the parentheses changes the signs inside, giving us 3x minus 5 plus 2x equals 0. Next, I'll combine like terms. 3x plus 2x equals 5x, so we have 5x minus 5 equals 0. Adding 5 to both sides gives us 5x equals 5. Finally, dividing both sides by 5, we get x equals 1. Excellent, we found our x value. Step 4. Now we back substitute to find y. We know that x equals 1, and from our earlier work, y equals 5 minus 2x. Substituting x equals 1 into our formula, y equals 5 minus 2 times 1. This simplifies to y equals 5 minus 2, therefore y equals 3. Perfect, now we have both values. Our solution is the ordered pair 1, 3. This means x equals 1 and y equals 3. Step 5. We should always check our solution by substituting both values back into the original equations. Checking the first equation, 2x plus y equals 5. Substituting our values, 2 times 1 plus 3. This equals 2 plus 3, which equals 5. Perfect. The first equation checks out. Now checking the second equation, 3x minus y equals 0, substituting 3 times 1 minus 3. This equals 3 minus 3, which equals 0. Excellent. Both equations are satisfied, confirming our solution is correct. Congratulations, you've successfully mastered the substitution method for solving systems of equations. This is a powerful algebraic technique that you'll use throughout your mathematical journey. Remember these key takeaways. First, always isolate the easiest variable. Second, substitute carefully using parentheses to maintain correct signs. Third, solve step by step without rushing. Fourth, always check your solution in both original equations. And finally, practice makes perfect. The substitution method is now part of your mathematical toolkit. With practice, you'll be able to solve systems of equations quickly and confidently. Keep working through problems, and remember that every mathematician started exactly where you are now. You've got this.